Good morning. Today we're going to discuss a topic that tends to baffle a lot of students in general chemistry, and that topic is stoichiometry, which is just the relationship between the reactants and products within a chemical reaction. Stoichiometry can be used to solve a lot of complex problems within a reaction, and today we're going to use stoichiometry to solve the problem of reaction yield. So for our example, we're going to take ammonia, react it with molecular oxygen to yield nitric oxide and water. Now, as you can see from the equation, it's unbalanced. Careful inspection of the equation will show that you need at least 4 moles of ammonia combined with 5 moles of molecular oxygen to yield 4 moles of nitric oxide, 6 moles of water. At this point, the reaction is what we call balanced. It is really, really important to have a balanced reaction for any type of stoichiometric problem. For our problem today, we're going to try to determine the theoretical yield of nitric oxide if we start with 100 grams each of ammonia and oxygen. Now, the first thing that we need to do for any type of stoichiometric problem is convert the gram amounts into their corresponding amounts of moles. So, I have 100 grams of ammonia. From the periodic table, I can determine the molar mass of ammonia, which is approximately 17 grams per mole. Divide by the molar mass, and you will see grams cancel with grams, and your final answer will be in moles. We do the same thing for molecular oxygen. Again, refer to your periodic table. You'll see that O2 has a molar mass of 32 grams per mole. Take 100 grams, divide by the molar mass. Round the grams to cancel out the grams, and I come out with the corresponding amount of moles. The next question we have to ask ourselves is, do we have enough of each reactant to take this reaction to completion? For that, we need to go back to the balanced chemical equation. And look at the relative amounts of ammonia to oxygen and vice versa. Now, I can see from my calculation that I have 5.9 moles of ammonia. This is the true value. Now, based on the molar ratio of ammonia to oxygen, I can see that for every 5 moles of oxygen, I'm going to need to react that with 4 moles of ammonia. Now, if I do the arithmetic and multiply 5.9 times 5 and divide by 4, I'll come out with approximately 7.4 moles of molecular oxygen. Now, what exactly does that mean? Well, what that means is based on the original starting amounts. If I have 5.9 moles of ammonia, I'm going to need at least 7.4 moles of molecular oxygen to drive this reaction to completion. Now, the question is, how many moles of molecular oxygen do I have? Well, based on the starting amount, which was 100 grams, we only have 3.1 moles of molecular oxygen. So clearly, we don't have enough oxygen to complete the reaction. And we say that O2 is our limiting reagent. The limiting reagent is very, very crucial to understand in this type of problem, because the limiting reagent is going to dictate how much product we're going to actually be able to yield at the end. So now it's time to determine exactly how much product we're going to get. Now, we said that we have 3.1 moles of molecular oxygen. And again, this is the real value. Now we need to look at the molar ratio of our product, the nitric oxide, to the molecular oxygen. Again, this is why having a balanced equation is so important. If you don't have the balanced equation, you really can't determine the correct mole ratio. Now, looking at the equation, I see that for every 4 moles of nitric oxide produced, I had to have 5 moles of O2 to start with. Now, when we do the arithmetic, we see that moles of O2 will algebraically cancel out, and our final answer will be expressed in moles of nitric oxide. So, let's do the arithmetic. 3.1 times 4 divided by 5. And we should come out with approximately 2.48 moles of nitric oxide. This represents our theoretical yield. So again, the theoretical yield is the maximum amount of product that we can expect to derive based on the starting amount of reactants at the beginning of the reaction. Now, if you want to express the theoretical yield in terms of grams, that also is relatively simple. All we have to do is, again, refer back to your periodic table so that we can determine the molar mass of nitric oxide. And from the periodic table, we can see that nitric oxide has a mass of approximately 30 grams per mole. We allow the moles to cancel out. And doing the arithmetic with our trusty calculator, we come out with a mass of approximately 74.4 grams. And again, 74.4 grams is our theoretical yield. This time expressed in grams instead of moles. Thank you for joining us, and I hope this will help your study of stoichiometry.